Hey guys, I'm back with a new video. In this video we'll learn about decision tree classification algorithm. So till now we have covered the linear regression, logistic regression, KNN and the naive Bayes algorithm. We learned about linear regression, logistic regression, which are more of geometrical models that come under parametric methods because they have a functional form using which you can express these methods geometrically. Though logistic regression, as we discussed, also is a probabilistic method, as I discussed in the intuition video of it. So if you haven't checked out that video, the link for that video can be found down below this video. Then we have the KNN method, which is a non-parametric method. I discussed in the intuition video that it is an instance-based method and it takes into account all the points while making a decision for classifying a new unknown data point. If you haven't checked out the video on KNN algorithm, the link for that can also be found down below. Then comes the naive Bayes algorithm, which we discussed in the previous video. It too is a probabilistic method and we also covered the implementation for it using sklearn library. Now I would like to explain the concept of decision trees as easily as possible. Now let us try to relate the decision trees with a programming construct, which is the if-else statement that we are aware of. If you have ever programmed in any programming language, you must be knowing about conditional statements. KNN, as we know, is a heuristic method, but with decision tree, programmers feel home-like because it is very closely similar to an if-else conditional statement. So in a nutshell, you can say that the decision tree is very much similar to a nested if-else conditional statement. To explain my point, let us go over them now. But before that, let us understand what a decision tree is in a bit more depth. So a decision tree looks something like this, where at each such point, which is also known as a node, you take decision and based on that, you reach some other node. So here you can see we are using the outlook feature, and if the outlook feature is sunny, we reach this node. If it is overcast, we reach this node. If it is rain, we reach this node, and then further we can reach to these nodes, which are known as pure nodes because they are the leaf nodes of the entire tree. So now let us see what things we should be aware of while building a decision tree. First, let us talk about entropy. So let us suppose we are given a random variable y and it can take k values, y1, y2, y3, so on till yk. Then the entropy of y can be described as hy, and it is mathematically described by the formula negative of summation from I1 to k pyi into log pyi base b. So this is the formula for entropy. Now what do you mean by pyi? Let us understand this. Pyi is equals to probability that your random variable is some instance value yi. Now let us consider this data set. Suppose this variable, which is play tennis, is your random variable. So y is play tennis. It can take on two values, a yes or a no. All the yes represent the positive class and all the no's represent the negative class. So you can say P positive class denotes the probability of getting positive class data points in our dataset, which represent these yes values. And similarly, we can compute the probability of getting negative values or negative class data points in our dataset. Now how can we compute the entropy? So we can apply the formula that we just covered. So let us understand the properties of entropy. Now for understanding the properties, let us assume a simplistic class of binary classification where we have two classes, namely positive class and negative class. So let us first discuss the case 1. So case 1 is when you have 99% of points which belong to the positive class and 1% points that belong to the negative class. Which means that 99% of the points are positive and only 1% of the points in your dataset are negative. Then let us try to find the entropy for this variable, and this comes out to be hy minus 0.99, which represents negative of the probability of getting a positive class, which is 0.99, into log of 0.99 minus 0.01 into log of 0.01. So we are applying the formula that we discussed. So we are putting on the values for probabilities for each of the classes, for the positive class and the negative class. Then we are applying the summation, and finally we have the negative sign to get the final value of entropy for this case, and this comes out to be minus 0.08. So if we just consider the magnitude, it is somewhat closer to 0. Now let us discuss about the case 2. Now here again we have the same two classes. So probability of getting a positive class is 0.5 and probability of getting a negative class is again 0.5, which means that 50% of your data points are having the positive class and the rest 50% are having the negative class. And if we now try to compute the entropy, we get minus 0.5 into log 0.5 minus 0.5 into log 0.5. Now if you know the properties of logarithm, we know that log of 1 by 2 to the base 2 is negative 1. So this will get reduced to minus 0.5 into minus 1 minus 0.5 into minus 1. So this will be 0.5 plus 0.5, which is equal to 1. Now let us talk about the case 3, where again we have the two same classes, where we have 0 points pertaining to the positive class and 100% of the points or the entire dataset is having negative points in this case. And if you try to compute entropy for such a dataset where negative class is a dominant one, in that case you will get minus 0 into log 0 because we are not having any positive class, minus 1 into log 1. This 1 represents the probability of having a negative class into log 1. So in this case the entropy comes out to be 0. So what can we conclude from these three cases? From case 2 you can see that if both the classes have equal probabilities, meaning that 50% of your points in the dataset belong to positive class and the rest 50% belong to the negative class. That is, both the classes have an equal share of points of our dataset, then the entropy comes out to be maximum, which is 1. But from case 3, you can see that if one of the classes have all the points of dataset, that is, one of the classes is a dominant one, then the entropy comes out to be minimum, which is 0. So here you can see in this graph that when the probability of positive class is 0.5, which means the probability of negative class is also 0.5, because the probability of negative class plus probability of positive class is equals to 1. Therefore, if you have probability of positive class as 0.5, then probability of negative class will be 0.5 as well. And if the probability of positive class is 0.5 and the probability of negative class is 0.5, then you have the maximum value of entropy, which is Hy, represented by 1. Now if you go to the left side of 0.5, the entropy will tend to 0, because here what will happen is that the probability of positive class will become 0 when you reach at this point, and in that case the probability of negative class will be 1, which means one of the classes become dominant. And if one of the classes become dominant in case of binary classification, then entropy comes out to be 0. And if you reach to this end where probability of a positive class is 1, then in that case probability for negative class is 0. Again, one of our classes is dominant, which is positive class, and that is why the entropy reduces to 0. This curve holds true for only binary classification. For more than two class case, the equation for entropy is completely different, which we may discuss in a separate video if possible. So to conclude from this graph, the maximum entropy occurs when both the classes are equiprobable. When one class is more prominent than other one, in that case entropy will be minimum with a value of 0, which you are getting at these 2 points. Now if one of your classes go away from the value of 0.5, you are tending to an entropy of 0 in that case. Now let us take the k values case. So given a random variable y and it has k values, all of them are equiprobable, namely y1, y2, y3, yk, then your entropy is maximum. And for such a case, the graph looks something like this, where we are having a uniform distribution because each of our k values are equiprobable. So this is called a probability density function, where for each of your k values you are getting the same probability or they are equiprobable. Now in the next case, let us suppose given a random variable y that is having k values, suppose one of them is most probable, say y3, and all of others like y1, y2, y4 have a probability of 0, then entropy will come out to be minimum in this case. Now let us understand more on entropy using this probability density function. So you can see we are having the random variable y that is taking all these values starting from a and going till b, and let probability density function be along the y-axis. So this is like a uniform distribution. As you can see, all the values from a to b have the same probability, and therefore in this case entropy is also maximum. Now let us consider another example. Here I have a Gaussian distribution curve which looks something like this. Now in the two graphs that you can see, the two curves that we are having, which is this green curve and this blue curve, you can see that the probability that b takes a small set of values is very high. So here you can see these orange circles represents a small set of values is being taken by B, while in case of A you can see it covers a broad spectrum of such points, which means that in case of A, which is the green curve, the values are much more spread, and we have seen that as we move towards the same probability case, the entropy becomes maximum. So given these two curves, we can easily deduce that entropy of B, which is the blue curve, is less than the entropy of A, which is h of B is less than h of A, where h denotes the entropy. So in case of A, we can see points in a much wider range, which is not the case with the B curve. So if a distribution is closer to uniform distribution, which in this case is shown by the curve A, then we have a higher entropy compared to the curve which is far away from a uniform distribution, as shown by this blue curve, which has a lower entropy value. So the curve B, being more peaked, is having a lower value of entropy, and the curve A is less peaked. That is why it is having a higher value of entropy, because it covers a wide spread of points. So it is less peaked, and as a result of being less peaked, it has a high value of entropy. Now one thing you can clearly see from this curve is that more peaked a distribution is, less is the entropy. If one of the values dominate, like shown in this peaked distribution, then the entropy is minimum. Now let us move further and understand the concept of information gain. Now consider this entire dataset where we are having some features, and here we are predicting whether we can play tennis or not. So the features that we are having is outlook. Outlook can take three values: sunny, overcast and rainy. Then we have temperature that can take hot, mild and cool. Then we have humidity, which is high, normal. Then we have windy, false and true, so it takes a Boolean value. And then we have to predict whether we can play tennis or not. So this is the simple dataset that we will cover in this video. Now let us consider outlook as the root node of the decision tree, and here we care about the class label y, which can either belong to positive class or the negative class, right? At the root node, it is given that entropy is 0.94. So we are taking outlook as the root node of the decision tree. The entropy of entire dataset before the split is this, and this we are getting by this. Let me show you. So you can see that we are having 9 positive points which are having a value of yes for play tennis, and 5 negative points which are having a value of no for play tennis. So if we apply the formula for calculating entropy, so for 9 positive points out of 14 points, so 9 out of 14 points are positive. So this represents the positive case where the probability of getting a positive class is 9 by 14. Then we are taking log of it, we are multiplying both of them and taking negative of that. Then same for negative class, and this is the same formula that we had discussed for entropy just a while back. So this comes out to be 0.94. So at the decision tree, we are having an entropy value of 0.94. So now suppose we decided to split that decision tree based on the outlook variable, and you can see here that output variable has 3 possibilities, namely sunny, overcast and rainy. So we are splitting our entire dataset into 3 subsets. So let us reference each of these datasets as dataset 1, dataset 2 and dataset 3 respectively. So first let us find the entropy on class label y for dataset 1. We first need to count the number of positive outcomes and the number of negative outcomes. So we are having 2 positive outcomes and 3 negative outcomes. So let us check this out. So 2 positive outcomes out of 5 and 3 negative outcomes out of 5. So this is the probability. So 2 by 5 is the probability of having a positive class, and 3 by 5 is having the probability of a negative class. We are applying the formula for entropy, and this comes out to be 0.97 for the first subset that we got after the split on the outlook variable. Now let us move on to the second subset. Here you can see we are having all the positive outcomes, which means that one of our classes is dominant. So if you go by the concept that we covered just a while back, in this case the entropy should come out to be equal to 0, and it is indeed 0. So let us see how we get to it. So it is minus 4 by 4, which means probability of having positive class points, which is 1 because all of them are positive, and negative points are 0. So this reduces to 0, and this is minus 1 log 1. So 4 by 4 is 1, and log 1 to any base is 0. So this comes out to be equal to 0, which means for this subset the entropy is minimum. And finally to the last subset, which is dataset 3. Here you can see that we are having 3 positive outcomes. We have 3 yes and 2 no's. That is 2 negative outcomes. So if we compute the entropy in this case, we'll get minus 3 by 5 into log 3 by 5 minus 2 by 5 into log 2 by 5, which comes out to be equal to 0.97. Now if you try to compute the average entropy after the split, this comes out to be equal to 0.64. So you can say 0.97 plus 0 plus 0.97. This comes out to be roughly equal to 0.64 something, which we can get by saying 0.97 plus 0 plus 0.97 divided by 3. So this is roughly equal to 0.64. So if we compute information gain for class label y, when you split the dataset on the outlook feature, this will come out to be equal to entropy of the entire dataset before the split of the dataset minus summation of entropies that we get right after the split of the dataset on the outlook feature, so which is 0.94 minus this term. Now if we compute the summation of entropies that we get right after the split, now this will be equal to 5 upon 14 into whatever entropy that we get for this subset, which is 0.97 plus 4 by 14 into 0 for the second subset, and for the third subset it is 5 by 14 into 0.97. So if you calculate this completely, you will get 0.25 as the information gain. So now we have seen how we can compute the information gain. So let us see how we can use information gain in construction of decision tree, and you can extend the same way of computing information gain to n such splits. Now let us talk about the concept of something called as Gini impurity. Now Gini impurity is something that is very similar to entropy. So the formula for this is GIY, which represents the Gini impurity, 1 minus summation of probability yi from 1 to k. Now where your random variable y can again take k values. Now consider the case of binary classification where a random variable can either take a positive outcome value or a negative outcome value. So let us restrict ourselves to the case of binary classification where we have only 2 outcomes, a positive outcome or a negative outcome. So let us take the case when probability of having a positive class is 0.5 and probability of having a negative class is 0.5. That is, both the classes are equiprobable. In that case, you know that entropy is maximum, so we are getting 1. But if you compute the value of Gini impurity, that will be 1 minus 0.5 whole square plus 0.5 whole square. So we are squaring both of these probabilities and adding them and then subtracting them from 1. So this gives us 0.5. If we do the same thing for the second case where probability of having a positive class is 1 and probability of having a negative class is 0, that is one of the classes is dominant, then you know that if one of the classes is dominant in case of binary classification, then your entropy is minimum, which is 0. And if you apply the squares on each of these probabilities and then subtract their sum of squares from 1, you get 1 minus 1, which is 0. So here Gini impurity is 0. So for a binary classification case, the curve for entropy and Gini impurity looks something like this. So what can you deduce from this curve? As probability for positive outcome increases, that is along the x-axis, if the probability is increasing, say from 0.5 to 1, so it is tending from 0.5 to 1, or say this interval from 0 to 0.5, both the entropy and the Gini impurity increases but at different rates. And if you take the interval from 0.5 to 1, both the entropy and the Gini impurity decreases, this time again at different rates. Now as a side note, the reason for computing Gini impurity is that it requires less computation power than what is required in computing entropy. So now we know about the concepts of entropy, information gain and Gini impurity. Let us move forward and understand how we can construct a decision tree. Now consider the same dataset that we have, where we have 9 positive points which are represented by these yes and 5 negative points which are represented by no's. It is given that entropy for our class label with respect to the entire dataset is 0.94 that we computed earlier. Now for the given dataset, we can split it based on any of the 4 features, based on outlook or based on temperature, based on humidity or based on windy. If we split the dataset based on the outlook feature, then we know that before the split of the dataset, we have an entropy value of 0.94. If we consider the weighted entropy of each of the 3 subsets that we are having, so one subset is this, other subset is this, and the third subset is this, or you can understand this from this example. if we consider the weighted entropy of each of the subsets that we got after splitting our dataset based on the outlook feature, you saw that we got a value of 0.69 as the weighted entropy, which we got by taking the average of these three entropies, right? So the information gained for our dataset when the split out dataset was based on the outlook feature comes out to be equal to 0.25 that we earlier saw. Now you can also break your dataset based on temperature feature. You can see temperature has three values: hot, mild and cool. If we split it based on the hot value of temperature, just focus on hot values of temperature, that for hot value of temperature we are getting 2 positive points and 2 negative points. If we split it based on mild value of temperature, so just focus on mild value, here you can see we are having 4 positive points and 2 negative points. And in the same way we can also split our dataset based on the remaining two features like humidity and windy. So humidity can be split based on high and normal, and windy can be split based on these two booleans, so false or true. Now as a side note, here you can see we are having a node that is having 4 positive points, so 4 yes, and 0 negative points, which means there is no need of breaking it further. So here we are having outlook as overcast. Let us refer the decision tree. So this is the case where we are getting 4 positive points and no negative points. So we are getting a yes that you can play tennis when outlook is overcast. Now once you achieve this condition, when all of your points are either positive or negative, that is one of the classes is dominant, which means your entropy is minimum. At this very point you get a pure node. So this node is called a pure node. Each of these green nodes are called pure nodes. Now once you get the pure nodes, there is no need of breaking it further, and hence it is termed as a pure node because further splitting is not possible. While at the other two nodes, if you take these nodes, which is represented by humidity and windy, we can still make the splits. Let us now split the left node, which is this one, which we got from outlook as sunny, and let us split this on the basis of humidity. So focus on this subset based on humidity. You can see when the humidity is high we are having 3 no's, and when the humidity is normal we are having 2 yes. So when humidity is high we are having 3 no's and 0 yes, and when the humidity is normal you are having 2 yes and 0 no's, which means again you have achieved pure nodes and further splitting is not possible. So this branch is now done, and the middle one is also done. Now if we see this one, now let us do the same process over the rightmost node as well. So let us focus on the third subset that we get right after the split, which is this one. Now when windy is false you are having 3 yes, and when windy is true you are having 2 no's, which means that when windy is false all of your points belong to positive class, and when windy is true all of your points belong to negative class, which means this is a case of one class domination, and that is why the entropy becomes minimum. So here one of the classes is dominant, and that is why you have reached the pure node situation again. Now if windy is true then we get 2 no's, here you can see this, and 0 yes. So we have again reached the condition of pure node where only one of the classes is dominant and the other one is absent. So this is how we construct the entire decision tree. So I hope that everything makes sense. So we recursively keep going down and down until we get a pure node where either we have a positive class or a negative class, but not both. So once you reach at the level of pure nodes, only one of your classes will be dominant. So this is all about splitting that I wanted to cover in this video. In the next video I will discuss about the concept of overfitting and underfitting, because it is very much possible that for a decision tree, for example, if it goes too deep, overfitting may occur because of noisy points, and for a smaller height of tree, underfitting can occur. Let's catch up in the next one.